what I would like to do now is in approximately 10 minutes, review the entire quarter for you. And it's, I think, very useful because this course, more than any, is basically all the math you need to do all the linear physics that shows up in physics courses. We mentioned occasionally nonlinear systems and all of that. We don't really do any of the math associated with nonlinear systems. But basically, everything we focused on, if you go back and look, comes down to something that's useful for linear operators, which were defined by acting like this on some objects and with a scalar like that. And for things that are basically elements of a linear vector space. And I'm not going to give all the rules of defining the vector space, but the key ones is that if you add them, you're still in the space. If you multiply by a scalar, you're still in the space. And of course, we have a negative and an inverse. This is the lens through which you want to look at everything we did in this course. Everything we did in this course should somehow connect back to these ideas for you. And I want to go through this kind of in 3 pieces. So we spent a lot of time in various forms dealing with the idea of a basis. This is why we started off with the idea of a series expansion as the very first thing we did. Because fundamentally, at the end of the day, we talk about our vectors. When we want to do computation, we convert them to a basis. Converting them to a basis is a series expansion of coefficients times basis vectors. That's why we use series in physics, really, at the end of the day. And if it's an infinite situation, we like to approximate things by the ones where the coefficients are big and ignore the small coefficients. And this is the whole idea in a lot of image processing. It's the whole idea behind a ton of stuff, right? If I want to do image compression, what do? Instead of taking megapixels, which is real space, and telling you the value at every point in space, which is what type of basis? No. If I'm giving you the value of a function at every point in space, what have I chosen to use as my basis? It's infinite, but I've chosen my delta functions, my value at every point in space. Now, if that image has natural normal modes, and there's a finite number of them, instead of representing that image by a value at every point in space, I can represent that image by a value for each of the normal modes. And for some images, I could go from megapixels down to 5 numbers with the right picture. So depending on the picture, you get better or worse image compression. Now, to do this, anytime we want to find our components, the main idea we use is what?
Projection.
Projection. And that played a central role throughout the course. So we have to understand what is the scalar product in any given situation. And this is where the Bronquet notation becomes so powerful for basically abstract manipulation. It works for keeping track of things really well, keeping track of what your basis vector is, keeping track of the fact that if we're using complex numbers, we want a complex conjugate. If we're using an infinite basis, we're going to do an integral. It's a really great shorthand. Then at the end of the day, if it's a discrete situation, you'll convert to column vectors and row vectors to do the calculation. And if it's continuous functions, it's almost always an integral. And finally, since what we want are orthogonal basis, the idea of Hermitian operators came in. And this was really important in the transition to looking at ODEs and PDEs as part of a linear basis. right? Knowing that the operators themselves were Hermitian gave us the fact that the solutions were eigenfunctions that were orthogonal, that could be used as a basis, which allowed us to do series expansions like Fourier series and other series expansions. And so this was a thread going throughout the course. And as you study and review this material, this is a course where it's really important to see those connections, I think. We've taken all the math you've learned in 2 years and tried to really provide these connections that may not have been obvious when you first saw it, that are going to be critical to picking the right math tool when you're faced with a physics problem, where they don't tell you which math tool to use to solve it. Now, the second big idea I'm going to call phase. And that's the one we didn't quite do enough with at the beginning. So we came back to it in the middle of the course. So now hopefully there's enough. But if things are linear, there's 2 pieces about that. A linear operator tends to just change, by definition, the amplitude and the phase of the thing it acts on. And so understanding how to keep track of things using complex notation is important. And this is one place where we're thinking of phase kind of as a mathematical trick, in a sense. It's allowing us to do the math easier. We're using the fact also, if you recall, that the linear operator acts independently on the real and imaginary part because of the L of A plus B equals L of A plus L of B. And so we can do things like take a cosine and write it as the real part of an imaginary number. But there's something also more important about phase. In quantum mechanics, the phase is real. The phase matters. The wave function is inherently a complex number. We measure the modulus squared, but the wave function itself is complex. And you need to know about the phase. And dealing with all sorts of wave behavior, understanding that this piece here is the phase that basically tells us where we are in the wave. Is key. And the number of situations, because we're dealing with linear differential equations, that plugging this in and looking at omega as a function of k and dispersion relations and really thinking about the world in terms of plane waves, e to the I kx's, because it goes back to superposition, which is another feature of linear systems, that I can add these up, which I'm going to talk about next, and make wave packets. This whole role of phase is central. And so that's why it's really important to make sure you go back to the beginning of the course and you go back to that additional lecture in the middle, and you really understand why we care about understanding the structure of e to the I phi and its relation to cosines and sines so deeply, because it's one of our primary mathematical tools in linear systems. The final piece really is really understanding how we use integration. And I think this is something that really will only become clear now. But I said before that integration is basically the idea of summing up pieces. Well, linear systems have the fundamental feature that you can do superposition. Right? If I go back to my definition, if I think of this as a linear system I'm trying to solve for, if A is a solution and B is a solution, then L of A plus B being L of A plus L of B will also be a solution most of the time. Because if I'm solving the linear system acting on something equals 0, in particular, if L of A is 0 and L of B is 0, then L of A plus B has to be 0 by that top equation. And so when I'm solving linear operator acting on stuff equals 0, the homogeneous equations, then superposition becomes my central tool. And in anything where I'm doing small stuff, then I'm doing an integral. If it's a continuous situation, my sum over finite things becomes an integral over dk's, an integral over d omegas, and so that's where we get wave packets. When you get into condensed matter, you have to understand phase space and phonons and electron spectrum, and you do a lot of integrating over phase space when you do stat mech, because the sums becomes integrals because the spacing becomes small. We also showed all of our examples where you have a dq or a dm or a di, and you add up your small pieces, and so you have a sum over one set of coordinate systems, creating a function over the rest of space. So really understanding that structure of why are we able to do this sum? Because electromagnetism is linear. And so the electric field of a charge distribution is the sum of the electric fields of the individual pieces. And that's why I'm allowed to do an integral. And it's fundamentally a linear system idea. And when we deal with integration, we have to understand that now we get the wonderful choice of either adding up the little pieces of the function around the boundary or adding up the derivative of the function. And this is really powerful with a lot of the vector cases. This was the one place we didn't do as many physical examples. I did a few. You know, we derived things like the flux idea, and we derived the continuity equation. And we saw how, considering the fact that the system's linear and I can sum pieces to get an answer, summing over the whole volume versus summing over the boundary, or summing over the area versus summing over the curve on the outside, really allows us to understand the physics, which comes back to I'm doing integrals because it's linear, and I'm summing stuff. And so it really helps with these vector situations, because a lot of times these are the challenging ones to construct and do. And that really is the course. And you hopefully, when you're done, you can see these connections to linear systems and think in terms of these higher ideas. So it's not just detailed rules for each special case. They're all fitting into some bigger picture. And so when you get an arbitrary physics problem and you recognize it's linear, you basically know you're going to use something from P50. That's what it's going to come down to, in a way.